Hello, and welcome to The Sleepy Scientist. I'm very glad you've joined me tonight. Before we wander too far into the universe, tell me where you're listening from. Maybe you're tucked into bed after a long day, stretched out somewhere quiet, or simply letting this play in the background while the rest of the world settles down. Wherever you happen to be, make yourself comfortable and let your mind wander for a little while. And if these slow journeys through science help you relax, a like and a subscription are always appreciated. They help this little corner of YouTube reach more curious night owls. And if you've been here before, thank you for coming back. I'm genuinely grateful that you choose to spend some of your evenings here. We also have an ebook available on the Sleepy Scientist website if you'd like to take these journeys with you. You can find it through the link in the description or by scanning the QR code on your screen. And if you'd prefer to rest your eyes completely, we're now uploading episodes to Spotify, so you can listen with your screen off and simply let the words carry you. Tonight, though, we're going somewhere rather difficult to picture. We can look across billions of light years, past distant galaxies and ancient light, but eventually our view simply runs out. And that leaves a wonderfully simple question with a surprisingly strange answer. If we could somehow keep travelling beyond everything we can currently see, would space continue forever? Could it curve back around? Or might there actually be some kind of end? Fortunately, there is no need to pack for the journey. So get comfortable, let everything else become a little quieter, and let's head outward. Does space ever actually end? When we ask whether space ever ends, the first difficulty is deciding what the word end is supposed to mean. It sounds simple enough. We are used to things having boundaries. A road ends. A coastline ends. A room has walls. A planet has a surface. Even the largest structures we encounter are still objects surrounded by something else. So it feels natural to imagine that if we travelled far enough through space, eventually we might reach some final location where there was simply nowhere left to go. But space is not an ordinary object sitting inside a larger room. There are several very different ideas that can hide inside the phrase the end of space. One possibility would be a genuine physical edge, some ultimate boundary where space itself stops existing. Another would be a universe containing only a finite amount of space, which sounds similar but does not necessarily require an edge at all. There is also the limit of the observable universe, beyond which we cannot currently see. And then there are cosmological horizons created by the expansion of the universe, which can prevent light or information from ever reaching us. These are not the same thing. The observable universe is particularly easy to mistake for the whole universe. From Earth, we can see an enormous region of reality containing hundreds of billions of galaxies, stretching across distances that are difficult even to imagine. Yet there is no reason to assume that the most distant thing we can observe marks the final boundary of existence. Our view is limited mainly because light travels at a finite speed and the universe has existed for a finite amount of time. The universe is about 13.8 billion years old. That does not mean the observable universe has a radius of only 13.8 billion light years, because space has been expanding while ancient light has been travelling toward us. The most distant regions whose ancient signals can reach us today are now much farther away than they were when that light began its journey. So when astronomers speak about an observable boundary, they are not describing a wall. There is no known cosmic fence sitting at the limit of our telescopes, perhaps with a polite sign asking visitors not to proceed any farther. Instead, we are encountering a boundary in information. Beyond a certain distance, light has simply not had the opportunity to reach us. This is already enough to make the original question rather stranger than it first appeared. But modern physics goes further, because space itself is no longer treated as a passive, rigid container. For Isaac Newton, space could be imagined as an absolute background in which events occurred. Objects moved through it, planets orbited through it, and the stage itself remained fixed. Albert Einstein's general theory of relativity transformed that picture. In general relativity, space and time form spacetime, and the geometry of spacetime is dynamical. Matter and energy influence its curvature, while that geometry influences how matter and light move. On the largest scales, the spatial geometry of the universe can expand, curve, and evolve. That immediately allows possibilities which everyday intuition is not well prepared for. Space might be infinite, extending without limit in every direction. But it could also be finite, without possessing any edge. A useful, although imperfect, comparison is the surface of Earth. The surface has a finite area, yet someone travelling across it does not eventually arrive at the end of the surface. Provided they keep going, they can continue around the planet. The analogy is only two-dimensional, whereas the space around us is three-dimensional, but it demonstrates an important principle. Something can have a finite size without needing a boundary. A finite universe could, in principle, have an analogous kind of global geometry. Travelling far enough might eventually bring an explorer back toward a region they had visited before. Although the actual possibilities for cosmic geometry and topology are considerably richer than the surface of a sphere. Alternatively, space may genuinely continue forever. Observations presently tell us that, on very large scales, the geometry of the observable universe is extremely close to spatially flat. That is compatible with an infinite universe, but it does not prove that the universe is infinite. Certain finite geometries can also appear locally flat if their total scale is much larger than the region available for us to observe. And this exposes one of the deepest difficulties in answering the question. Cosmologists can only directly measure the universe from which information has reached us. They can study distant galaxies, the expansion of space, the distribution of matter, and the cosmic microwave background left from the young universe. Those observations allow remarkably precise tests of cosmological models. But observations made inside a finite region cannot automatically reveal the complete global structure of all space. If the universe extends vastly farther than the observable region, we may be able to infer some of its properties without ever seeing its full extent. And if some regions remain permanently beyond causal contact with us, then there may be questions about the universe as a whole that no experiment performed from our region can completely settle. So the most accurate answer available today is both satisfying and slightly unfinished. No physical edge of space has ever been observed. Nothing in modern cosmology suggests that the boundary of the observable universe is a place where space suddenly stops. Everything we measure is consistent with space continuing enormously farther than the portion visible from Earth. What remains uncertain is whether that continuation goes on forever. The entire universe may be infinite. It may instead be finite but unbounded. Its global structure may possess properties that lie far beyond anything we can presently detect. So asking whether space ends does not lead us toward a distant wall. It leads instead toward geometry, relativity, observation, and one of the quietest mysteries in cosmology, whether the universe is merely unimaginably large, or whether there is, quite literally, always more space. The universe we can observe is enormous, but enormous is not the same as complete. When astronomers talk about the observable universe, they mean the region of space from which light, or some other signal travelling no faster than light, has had enough time to reach us. It is a limit set by time, distance, and cosmic expansion. It is not a statement about where space itself stops. The universe is roughly 13.8 billion years old. At first, it might seem reasonable to imagine that we should therefore be able to see no farther than 13.8 billion light-years in any direction. After all, if light has been travelling for 13.8 billion years, surely it could only have crossed 13.8 billion light-years. But the universe has not remained the same size while that light was travelling. Space itself has been expanding. Imagine a distant galaxy whose light began travelling toward the region that would eventually contain Earth billions of years ago. During that journey, the distance between us and the galaxy continued to change because the large-scale universe was expanding. The galaxy, therefore, does not have to remain at the same distance it was when the light first left it. As a result, some of the matter whose ancient light we receive today is now roughly 46 billion light-years away, in what cosmologists call present-day moving distance. That gives the observable universe a present diameter of roughly 93 billion light-years. It is a remarkable figure. If light could somehow cross that entire distance through an unchanging universe, the journey would take roughly 93 billion years. Yet even this vast region represents only the part of reality from which information has been able to reach us. It is not the measured diameter of the entire universe. That distinction matters enormously. The observable universe is centered on us, but this does not mean Earth occupies the center of the universe. It only means that we are the observers making the measurement. An astronomer living in a galaxy billions of light-years away would also find themselves at the center of their own observable universe. Their cosmic horizon would extend outward around their location, just as ours extends outward around Earth. Some regions visible to them might lie beyond our horizon, while some places visible to us could lie beyond theirs. Every observer effectively carries their own observable universe with them. This fits with one of the central assumptions of modern cosmology, known as the cosmological principle. On sufficiently large scales, the universe is treated as approximately homogeneous and isotropic. Homogeneous means that, averaged across very large distances, matter is not concentrated around one uniquely special region of space. Isotropic means that, again on sufficiently large scales, the universe looks broadly similar in every direction. Neither statement means that every location looks identical. Nearby space is obviously full of irregularities. Galaxies gather into groups and clusters. Vast filaments of matter weave through enormous cosmic voids. Some directions contain bright nearby galaxies, while others appear comparatively empty. But when these structures are averaged over sufficiently large scales, observations support a universe without an obvious privileged center. The fact that our observable universe appears centered on Earth, therefore, says something about observation, not cosmic importance. A useful comparison is the horizon you see while standing on Earth. From an open landscape, the horizon forms a boundary around everything you can currently see. Yet nobody would seriously conclude that the planet itself ends there. Walking toward the horizon does not allow you to reach a fixed line painted onto Earth's surface. The horizon changes as you move. The cosmological horizon is not created in exactly the same way. Earth's horizon mainly exists because the planet's surface curves away from your line of sight. The boundary of the observable universe arises from the finite age of the cosmos, the finite speed at which signals travel, and the expansion of space. Still, the analogy captures one important idea. A boundary to what you can see is not necessarily a boundary to what exists. Beyond our observable universe, there may be more galaxies, more galaxy clusters, more dark matter, more enormous voids, and more regions of space following the same broad physical laws we observe here. we cannot directly inspect their present condition. No photograph can show us what is happening right now in a region from which present-day information has not had time to arrive. But the simplest large-scale cosmological models do not suggest that the universe abruptly changes character at the limit of our vision. There is no known reason for galaxies to stop existing simply because their light cannot reach Earth. In fact, the boundary of the observable universe does not correspond to any obvious physical landmark at all. If you could somehow be transported to a distant location near what we currently call our observational horizon, you would not expect to find a cosmic wall waiting there. From that new location, the universe would open around you again. There would be regions behind you, regions ahead of you, and a new, observable horizon centered upon wherever you happen to be. This is why the phrase observable universe has to be handled carefully. It describes our accessible region of the cosmos, not necessarily the whole of creation. The roughly 93 billion light-years we can place within our present observational sphere may be a tiny fraction of everything that exists. Space could extend somewhat farther, vastly farther, or perhaps without limit. At present, we simply do not know its total extent, and so the most distant thing we can see should not be imagined as the final thing there is. Our telescopes eventually reach a limit, but that limit belongs to observation. It does not yet appear to belong to space itself. The Big Bang is often imagined as the largest explosion that could possibly occur. A tiny point somewhere in darkness suddenly erupts, throwing matter outward into empty space until stars, galaxies, and eventually everything we know appears inside the expanding debris. It is an understandable picture. It is also not what modern cosmology means by the Big Bang. The Big Bang was not an explosion at one location in an already existing universe. There is no known point in space where the explosion happened, and there is no direction we could travel to find the place where everything began. Instead, the Big Bang describes an early state of the universe in which matter and radiation were extraordinarily hot and dense, and in which the distances between widely separated regions were much smaller than they are today. Space itself was involved in the expansion. This distinction emerged gradually as scientists began applying Albert Einstein's general theory of relativity to the universe as a whole. General relativity had shown that spacetime was not simply a fixed background. Its geometry could respond to matter and energy, and that opened the possibility that the geometry of the entire universe could change with time. One of the first people to explore this mathematically was Alexander Friedmann. In the early 1920s, Alexander Friedmann found solutions to Albert Einstein's gravitational field equations in which the universe was not static. Depending on its contents and geometry, it could expand or contract. A few years later, Georges Lemaitre independently developed an expanding cosmological model and connected it with astronomical observations. Georges Lemaitre understood that if the universe is expanding now, then running that expansion backward suggests that the cosmos was once much denser. These ideas were initially surprising because even Albert Einstein had previously favoured a static universe. Observations soon provided strong evidence that cosmic expansion was more than a mathematical curiosity. Astronomers had discovered that the light from many distant galaxies is shifted toward longer, redder wavelengths. This cosmological redshift can occur because the space through which the light travels expands, stretching the wavelength along with it. Work by Vesto Melvin Slipher provided important early measurements of galaxy redshifts, while Edwin Hubble later combined distance estimates with measurements of recession to show that, in general, more distant galaxies are receding from us more rapidly. This became one of the observational foundations of the expanding universe. But the word receding can easily bring the explosion picture straight back. If every distant galaxy appears to be moving away, it seems natural to ask where they are all moving away from. The answer is that, on the largest scales, they are not simply racing outward from a central location through static space. The distances between widely separated galaxies are increasing because the scale of space itself changes with time. Imagine a collection of galaxies separated by enormous cosmic distances. If the scale of the universe increases, the distance between those galaxies can grow even if none of them has a special outward direction pointing away from some universal centre. This is why standard cosmology does not place Earth at the centre of the expansion. An observer in another distant galaxy would also see sufficiently remote galaxies generally receding. From that observer's perspective, the pattern would again appear centred on their own location. No contradiction is involved. A common way of visualizing this is to imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot becomes farther from every other dot. A dot does not need to occupy the center of the surface for the surrounding dots to move away from it. From the viewpoint of any chosen dot, the others appear to recede. The surface itself has no preferred central point. The analogy is useful, but it has to be handled carefully. The balloon surface is two-dimensional and is embedded in the three-dimensional space around it. Our universe has three spatial dimensions, and the analogy does not imply that the universe must be expanding into some enormous higher dimensional room. The outside of the balloon is part of the analogy, not part of the standard cosmological model. We only need the surface to understand the important point. Expansion can happen everywhere without having a centre within the expanding space. Running this expansion backward, therefore, does not cause all galaxies to converge toward one special location somewhere in the modern universe. Instead, the distances between regions become smaller everywhere. If we could trace the matter around us sufficiently far into the past, the material now forming our galaxy would have occupied an extremely hot and dense environment. But the same would also be true of the matter now found in distant galaxies. The Big Bang happened here. It also happened in the region now occupied by the Andromeda galaxy. It happened in regions billions of light years away. More accurately, the early hot and dense state filled the space represented by the cosmological model. There was no surrounding emptiness waiting for it to expand into. This becomes especially important when wondering whether space has an end. If the universe had begun as an explosion at one point, we might imagine travelling through space until we eventually found the centre where it began. Or perhaps travelling in the opposite direction towards some outer frontier reached by the expanding debris. Neither expectation follows from modern cosmology. There is no known cosmic crater marking the site of the Big Bang. There is no privileged direction leading back toward the origin. Wherever we are in the universe, looking far enough into space also means looking backward in time, because distant light has taken so long to reach us. In every direction, sufficiently ancient observations reveal a younger universe. The beginning is therefore not hidden at one distant location. It lies in the past of every region we can observe, and that quietly changes the question of where space ends. The universe did not begin by expanding outward from somewhere into surrounding emptiness. Space on the largest scales has been changing from within its own geometry. So travelling far enough would not bring us to the place where the Big Bang occurred. Wherever the journey began, that place was already part of it. Once we accept that the universe is expanding, another question appears almost immediately. What exactly is it expanding into? The instinctive picture is difficult to avoid. If a balloon grows, it expands into the air around it. If a cloud spreads, it occupies more of the surrounding atmosphere. If an explosion grows larger, the debris travels outward into space that was already there. So if the universe is getting bigger, it seems reasonable to imagine some larger emptiness waiting outside it. But modern cosmology does not require such an outside. The expansion of the universe is described from within the geometry of space itself. What changes is the distance between sufficiently separated regions of the universe. There does not have to be an external room for those distances to increase. One of the simplest ways cosmologists describe this change is with something called the scale factor. The scale factor is not a physical object. It is a mathematical quantity used to describe how characteristic cosmic distances change as the universe evolves. Imagine two galaxies so widely separated that they are not gravitationally bound to one another. At one moment, there is some distance between them. Later, after the universe has expanded, that distance may be larger. The scale factor tells us how the overall cosmic scale has changed between those moments. If the scale factor doubles, then two idealized locations participating fully in the cosmic expansion would become roughly twice as far apart. This does not mean that everything doubles in size. Your body does not expand with the universe. Neither does Earth, the solar system, or the Milky Way in any significant way. Electromagnetic forces hold atoms and molecules together, while gravity binds planets, stars, galaxies, and many galaxy systems strongly enough to resist the extremely gentle expansion occurring across comparatively small distances. Cosmic expansion becomes important across vast stretches of space where those local binding forces no longer dominate. The mathematical framework normally used to describe this is the Friedmann-Lemaitre-Robertson-Walker class of cosmological models. These models combine Albert Einstein's general theory of relativity with a large-scale assumption that the universe is approximately homogeneous and isotropic. In other words, once we zoom out far enough, no enormous region appears to occupy a uniquely privileged position, and the universe looks broadly similar in every direction. Within this framework, expansion is built directly into the geometry. This helps explain an important difference between ordinary motion and cosmological recession. If a spacecraft passes Earth, we can describe it as moving through local space. Its velocity has the familiar meaning of an object changing position relative to nearby objects. Very distant galaxies are more subtle. They can certainly have their own local motions, but much of the recession we observe at enormous distances arises because the metric distance between large-scale cosmic locations increases as the universe expands. Metric distance is simply the distance defined by the geometry of spacetime. The galaxies are not necessarily racing through static space like pieces of shrapnel after an explosion. Instead, the amount of space separating them changes. This is also why extremely distant galaxies can have recession rates corresponding to increases in distance greater than the speed of light. At first, that sounds as though it should violate Albert Einstein's special theory of relativity. Special relativity tells us that no material object can locally travel through space faster than light, and that rule remains intact. A galaxy in its own local region is not overtaking a nearby beam of light at some impossible speed. The apparent difficulty arises because cosmological recession across enormous distances is not simply ordinary local motion through one fixed background. General relativity allows the geometry separating distant locations to evolve, so two sufficiently distant galaxies can become separated at a rate corresponding to more than the speed of light, without either one locally breaking the light speed limit. This distinction is important because it reveals just how misleading familiar pictures of expansion can become. We tend to imagine that there must be something outside the expanding universe, because everything else we have ever watched expand already existed inside a larger space. But the universe is not merely another object of that kind. General relativity describes geometry intrinsically. That means the properties of a space can be discussed using measurements made entirely within that space, without first embedding it inside something larger. Distances, curvature, angles, and expansion can all be defined without identifying an external container. The surface of Earth offers a limited but useful analogy. Someone living entirely on the surface can measure distances, draw triangles, detect curvature, and determine that the surface has a finite area. None of those measurements requires the traveller to use the surrounding three-dimensional space as part of the geometry they are studying. Our universe is not simply the surface of a giant four-dimensional sphere, and the analogy should not be stretched that far. Its purpose is more modest. Geometry does not always require an outside in order to make sense. The same is true of expansion. If the distance between large-scale locations increases, then the universe is expanding in the cosmological sense. Nothing in that statement requires the universe to push into a surrounding emptiness. This also means that expansion does not automatically create an outer frontier. There is no requirement for some leading edge of the universe to move outward into unknown territory. If space is infinite, then an expanding universe can remain infinite while distances within it grow. Infinity does not have to become a larger infinity in the everyday sense. The separation between particular locations simply changes. And if space is finite but unbounded, it can still expand without developing an edge. Its total volume can increase, while every point remains part of a continuous geometry with no final wall. So asking what the universe is expanding into quietly introduces an assumption that modern cosmology does not need. It assumes that the universe must behave like an object inside something larger. General relativity allows a different possibility. Space can expand because its own geometry changes. And once that is understood, the idea of an expanding universe no longer implies an advancing boundary somewhere far away. Growth and edges are separate questions. The universe may become larger without ever growing toward an outside at all. One of the most difficult ideas in cosmology is that space could contain a finite amount of volume without ever coming to an edge. At first, that sounds contradictory. If something is finite, we usually expect it to stop somewhere. A table has edges, a field has boundaries, an island eventually meets the sea. Even a planet, however large, has a surface beyond which the solid ground ends. So if the universe contains only a finite amount of space, it is tempting to imagine some final boundary where the cosmos simply runs out. But geometry allows another possibility. A space can be finite and still have no boundary at all. The easiest way to begin seeing this is to think about the surface of Earth. Earth's surface has a finite area. There is only so much of it. And yet a traveller moving across that surface does not eventually reach a final line where the surface stops. If they continue far enough in one direction, they can eventually return to where they started. The surface is finite, but unbounded. That idea became much more powerful in the 19th century through the work of Bernhard Riemann. Bernhard Riemann helped develop the mathematics of curved geometry, extending geometry beyond the familiar flat rules associated with Euclid. In ordinary flat geometry, parallel lines remain parallel. Large triangles behave according to familiar rules. Distance works the way we are used to experiencing it across small regions of everyday life. Curved geometry is different. The geometry itself can possess curvature, and that changes the relationships between distance, direction, and shape. These ideas later became essential to Albert Einstein's general theory of relativity, where gravity is described through the curvature of spacetime. Once geometry is allowed to curve, our ordinary intuition about size and boundaries becomes less reliable. The surface of Earth provides a simple two-dimensional example. If you were a tiny creature that could only move along the surface and had no awareness of the third dimension, your entire universe would appear locally almost flat. Walk a short distance and nothing seems particularly strange. Draw a small triangle and its angles will add up almost exactly as expected in flat geometry, but travel across enormous distances and the curvature becomes impossible to ignore. The surface closes back on itself. You can keep travelling without finding an edge, even though the total area available to you is finite. Something loosely analogous can happen in three-dimensional space. A universe with positive spatial curvature could, in principle, possess a finite total volume while remaining completely unbounded. There would be no wall, no cliff, no final coordinate beyond which space ceased to exist. An explorer travelling continuously through such a universe might, under the right global geometry, and if cosmic expansion and practical travel limitations could somehow be ignored, eventually return toward the region from which the journey began. That does not mean our universe is known to have this form. It is one of several possibilities allowed by cosmological geometry. And there is an important caution hidden inside the familiar Earth analogy. When we picture the curved surface of Earth, we naturally imagine the planet sitting inside three-dimensional space. That can make it seem as though a curved three-dimensional universe must also be bent around inside some larger fourth spatial dimension. But this is not required. Curvature can be described intrinsically. That means observers can detect and describe curvature entirely through measurements made within their own space, without needing access to any higher dimensional outside. On Earth's surface, for example, one way to reveal curvature is to create an enormous triangle. Near the equator, imagine travelling north along one line of longitude until reaching the North Pole, then moving south along another line of longitude and finally returning along the equator. The angles of such a triangle can add up to more than they would on a flat sheet. An inhabitant confined to the surface could therefore discover that their geometry was curved without ever stepping away from it. In the same general spirit, cosmologists can study the geometry of our universe using measurements made entirely from within it. Positive curvature would mean that, on sufficiently large scales, spatial geometry behaves somewhat like the three-dimensional analogue of a spherical surface. The word spherical is useful mathematically, but it should not be taken to mean that the universe is a giant ball with empty space surrounding it. The geometry itself is what matters. This also introduces an important distinction between local appearance and global structure. Earth looks flat when you stand in a garden. It still looks almost flat when you travel across a city. The curvature only becomes obvious across much larger distances. A similar principle applies cosmologically. If the universe has positive curvature, but the radius of that curvature is enormously larger than the observable universe, then the region available to us could appear extraordinarily close to flat. That would not prove the whole universe was actually flat. It would mean only that its curvature was too gentle to become obvious across the portion we can measure. This is one reason the total size of the universe remains so difficult to determine. We can study the geometry of the observable cosmos with remarkable precision, but the observable cosmos may be only a small fraction of the whole. If the entire universe curves back on itself across distances vastly greater than those we can see, then its finite nature might remain hidden from us. And even if future observations established that the universe has a finite spatial volume, that discovery would not necessarily reveal an end of space. There might still be nowhere that space simply stops. A traveller could continue onward without encountering a boundary. The universe could contain only a limited amount of space while having no outer edge at all. That is the strange but perfectly valid lesson geometry offers us. Finite does not always mean bounded. And the question of whether the universe has a limited size is therefore not the same as asking whether space has an end. Once space is allowed to have geometry of its own, the question of its overall shape becomes unavoidable. In modern cosmology, there are three idealized possibilities for the large-scale curvature of space. Space can have zero curvature, it can have positive curvature, or it can have negative curvature. These names sound slightly abstract, but each one describes a different way that distances, angles, and large-scale paths can behave across the universe. The most familiar case is zero curvature, usually described as flat space. Flat does not mean that the universe is shaped like a sheet. It means that on large scales its geometry follows the ordinary rules associated with Euclid. In flat geometry, parallel lines remain parallel. If you draw a sufficiently large triangle, its three interior angles add up to 180 degrees. The relationship between the radius and circumference of a circle follows the familiar expectations of ordinary geometry. This is the kind of space that most closely matches everyday intuition, because the regions we experience directly are small enough that any cosmic curvature is far too subtle to notice. But space does not have to behave this way on the largest possible scales. The second possibility is positive curvature. A useful analogy is the surface of a sphere. On a sphere, lines that begin parallel can eventually converge. Imagine two travellers setting off northward from different locations on Earth's equator. At first, their paths may seem parallel. But if both continue toward the North Pole, the distance between those paths steadily decreases until they meet. That cannot happen in ordinary flat geometry. Large triangles drawn on a positively curved surface also behave differently. Their interior angles can add up to more than 180 degrees. In cosmology, a positively curved three-dimensional space could allow the universe to have a finite total volume while remaining completely without an edge. This is one of the reasons positive curvature has always been so interesting when asking whether space has a finite size. If the geometry closed back on itself globally, then space could be limited in total extent without having any final border. The third possibility is negative curvature. This is often described using hyperbolic geometry. A common visual analogy is a saddle-shaped surface, although no ordinary two-dimensional picture can fully capture the geometry of a three-dimensional negatively curved universe. In negatively curved space, paths that begin parallel tend to separate from one another. Large triangles can have interior angles adding up to less than 180 degrees. The relationship between radius, circumference, and enclosed volume also differs from flat geometry. For example, a sphere defined by a certain radius can enclose more volume in negatively curved space than an equivalent sphere would contain in ordinary Euclidean space. The effect would be tiny across short distances if the curvature scale were enormous, but across truly cosmic distances, those differences could become measurable. Albert Einstein's general theory of relativity allows all three broad possibilities. The actual geometry depends on the contents and evolution of the universe. This relationship appears in the Friedmann equations, developed from general relativity by Alexander Friedmann and later connected with the work of Georges Lemaitre. These equations relate the expansion of the universe to its average matter density, radiation, spatial curvature, and other forms of energy. Historically, this led to a simple picture in which a universe containing enough matter might possess positive curvature and eventually stop expanding, while a universe containing less matter might be flat or negatively curved and expand forever. That picture is useful as a historical starting point, but it is no longer sufficient. The discovery of accelerated cosmic expansion changed the situation. Dark energy appears to contribute most of the present energy density of the universe, and its presence means that spatial curvature alone does not determine the ultimate fate of cosmic expansion. A positively curved universe does not automatically have to collapse. A flat universe does not automatically imply one unique future. Curvature and cosmic destiny have to be treated as related but separate parts of the cosmological model. There is another distinction that is even more important when asking whether space ends. Curvature is not the same thing as topology. Curvature describes how geometry behaves locally and across extended regions. Topology describes the deeper global connectedness of space. A universe can therefore be locally flat and still have a finite global structure. One mathematical possibility is a flat space in which certain distant locations are identified with one another, producing a repeating geometry. An observer travelling far enough in one direction could, in principle, return from another direction without ever encountering curvature along the way. This would be very different from an ordinary infinite Euclidean universe, even though both could appear flat in local measurements. So knowing the curvature of space does not automatically reveal its total size. Still, measuring curvature remains one of the most powerful tools cosmologists have. If observations showed strong positive curvature, that would make certain finite models of the universe much more plausible. If observations instead showed perfect flatness across all measurable scales, an infinite universe would remain a natural possibility, although finite flat topologies could still exist. And if the universe were negatively curved, the geometry would again place different constraints on its possible global structure. The challenge is that any curvature might be extraordinarily gentle. If the radius associated with that curvature is vastly larger than the observable universe, then our entire visible cosmos could occupy only a tiny region of the full geometry. A small patch of a giant sphere looks flat. The same basic difficulty can apply to the universe. This is why cosmologists study the geometry of space so carefully. They are not simply asking whether cosmic distances behave in an elegant mathematical way. They are trying to infer something about the size and structure of the entire universe from the small portion available to observation. And the answer remains subtle. Space can be flat, positively curved, or negatively curved. Any of those possibilities affects how we think about the universe as a whole, but none of them by itself guarantees the existence of an edge. Even geometry can tell us how space bends without necessarily telling us where or whether it ends. If the shape of the universe is not something we can stand outside and look at, then the obvious question is how we can possibly measure it. The answer begins with some of the oldest light in existence. This light is known as the cosmic microwave background. It was released when the universe was roughly 380,000 years old, during a period when the cosmos had cooled enough for electrons and atomic nuclei to combine into neutral atoms. Before that time, free electrons scattered light so efficiently that the universe behaved rather like a glowing fog. Once neutral atoms formed, light could travel much more freely. That ancient radiation has been moving through space ever since. As the universe expanded, the wavelengths of this light were stretched enormously. Radiation that originally had much shorter wavelengths is now observed mainly in the microwave part of the electromagnetic spectrum. Today, the cosmic microwave background arrives from every direction in the sky. It is not coming from one particular object. Instead, it represents a view of the young universe surrounding us in every direction, carrying information about conditions that existed more than 13 billion years ago. Its discovery came with one of the more charming accidents in the history of astronomy. During the 1960s, Arno Allen Penzias and Robert Woodrow Wilson were working with a sensitive radio antenna at Bell Telephone Laboratories in New Jersey. They detected a persistent background noise that seemed to come from every direction. They checked the equipment. They investigated possible sources of interference. They even dealt with pigeons that had taken an unfortunate interest in the antenna. The noise remained. The explanation turned out to be far more interesting than faulty electronics or overly ambitious birds. Arno Allen Penzias and Robert Woodrow Wilson had detected the cosmic microwave background, radiation that had already been predicted as a consequence of a hot early universe. That discovery became one of the strongest pieces of evidence supporting the modern Big Bang model. But the cosmic microwave background does much more than tell us that the early universe was hot. It also helps reveal the geometry of space. The radiation is extraordinarily uniform, but not perfectly so. Its temperature varies very slightly from one direction to another. These differences are tiny, typically measured in parts per 100,000, yet they preserve traces of small density variations in the young universe. Those slightly denser and slightly less dense regions eventually helped seed the enormous cosmic structure seen today. Galaxies, galaxy clusters, and the vast network of filaments stretching across the universe ultimately grew from these early irregularities under the influence of gravity. The pattern of fluctuations also contains something extremely useful for measuring geometry. Certain physical processes in the early universe produced characteristic scales. One important example comes from sound waves moving through the hot mixture of radiation and ordinary matter before neutral atoms formed. Gravity pulled matter inward toward denser regions, while radiation pressure resisted compression. The result was a pattern of oscillations in the primordial plasma. By the time the universe became transparent, those oscillations had created characteristic physical scales. In effect, the early universe left us a cosmic ruler. If cosmologists know approximately how large one of these characteristic patterns should have been, they can measure how large it appears across the sky today. The comparison reveals information about the geometry through which the light travelled. The idea is similar to looking at an object of known size from a great distance. Its apparent angular size depends on how far away it is and on the geometry between you and the object. In flat space, light rays follow the relationships expected from ordinary Euclidean geometry. In positively curved space, those relationships change in one direction. In negatively curved space, they change in the other. So the apparent scale of patterns in the cosmic microwave background becomes a test of spatial curvature. This is one reason increasingly precise measurements of the microwave sky became so important. The Wilkinson Microwave Anisotropy Probe, operated by the National Aeronautics and Space Administration, mapped the cosmic microwave background across the entire sky with much greater precision than earlier observations. It measured the tiny temperature variations and allowed cosmologists to constrain fundamental properties of the universe far more tightly. The Planck spacecraft, operated by the European Space Agency, later produced even more detailed measurements. Planck observed the microwave background at multiple frequencies, helping scientists separate the ancient cosmological signal from foreground radiation produced within the Milky Way and elsewhere. The resulting maps contain an extraordinary amount of information. From them, cosmologists can estimate the age of the universe, its matter content, the amount of dark matter, properties associated with dark energy, and the curvature of space. And the curvature result is particularly relevant to the question of whether space ends. Measurements are consistent with the observable universe being extremely close to spatially flat. That does not mean scientists have demonstrated that space is perfectly flat. Every measurement has uncertainty. A universe with a very gentle positive or negative curvature could still appear almost indistinguishable from flat across the region we can observe. This distinction matters because exact flatness is sometimes casually treated as proof that the universe must be infinite. It is not. An infinite flat universe is certainly one possibility, but a finite universe with a very large curvature radius could look almost perfectly flat from inside our observable region. And certain global topologies could even produce a finite universe while preserving local flatness. So observations of the cosmic microwave background do not yet tell us the total size of space. What they do tell us is that any large-scale curvature must be small across the observable universe. If the universe is positively curved and closes back on itself, then the radius associated with that curvature would have to be considerably larger than the portion of the cosmos we can directly measure, depending on the exact model being considered. That is already an impressive result. Human beings cannot step outside the universe. We cannot photograph its overall shape from some convenient external viewpoint. Instead, we measure tiny variations in ancient light that has crossed billions of years of cosmic history. From those patterns, we infer how geometry behaves across distances so large that ordinary intuition is almost useless. The universe does not provide us with a map showing its full boundary, but it does leave subtle clues in the oldest light we can see. And so far, those clues tell us that the space around us is extraordinarily close to flat, while leaving the full extent of the universe tantalizingly unresolved. A nearly flat universe sounds, at first, as though it should settle the question. If space is flat, perhaps it must simply continue forever. That is certainly one possibility, and it may even be the simplest one to imagine. In ordinary Euclidean geometry, flat space can extend without limit in every direction. There is no curvature bringing distant paths back together, no outer wall, and no final region where the geometry suddenly stops. Such a universe would have infinite spatial volume. No matter how far an observer travelled, there would always be more space ahead. But flatness alone does not actually prove this. The reason is that cosmologists have to distinguish between two different ideas: geometry and topology. Geometry describes the local rules of space. It tells us how distances behave, how straight lines move, how angles add together, and whether space possesses positive, negative, or zero curvature. Topology deals with something more global. It asks how the entire space is connected. And two universes can have the same local geometry while having completely different global structures. The simplest flat universe is ordinary infinite Euclidean space. Imagine continuing in one direction forever. There is no repetition, no return, and no boundary. The volume is unlimited, and every new region leads to another. This is the picture most people naturally associate with a flat universe. But there are mathematically possible flat spaces that contain only a finite total volume. The easiest way to approach the idea is by imagining a simpler two-dimensional world. Suppose a flat sheet were arranged so that leaving through one side caused you to reappear through the opposite side. Move far enough to the right, and instead of reaching an edge, you return from the left. Travel upward for long enough, and you eventually return from below. Locally, everything can remain perfectly flat. Parallel lines can remain parallel. Small triangles can still have angles adding up to 180 degrees. Nothing about the local geometry tells an inhabitant that the entire space has been connected in this unusual way, yet the total area can be finite. In mathematics, an analogous construction is associated with a torus. The familiar image of a torus resembles the surface of a donut, but that picture can be slightly misleading for cosmology because the curved donut shape comes from embedding the surface in ordinary three-dimensional space. The important feature is not the donut appearance, it is the way opposite directions can be connected. A three-dimensional version of this idea can be constructed mathematically. Such a universe could be locally flat everywhere, while possessing a finite total volume and no physical boundary. An observer travelling far enough in one direction could eventually return to the same region. There would be no edge to cross. Space would simply repeat through its global topology. This kind of space is sometimes described as multiply connected. That means that the global structure allows different paths through space to connect regions in ways that would not occur in ordinary infinite Euclidean space. The universe does not have to possess this topology. There is currently no convincing observational evidence that it does, but the possibility is important because it shows why measuring zero curvature cannot by itself establish infinity. An observer living inside such a finite flat universe might initially have no idea that space repeated. If the repeating scale were small enough, however, the pattern could eventually reveal itself. One possible clue would be repeated images of the same distant astronomical object. Light from a galaxy could, in principle, travel along different paths through the global geometry and reach an observer from different directions. The same physical galaxy might then appear in multiple places across the sky, viewed at different stages of its history depending on the lengths of those light paths. Searching for such repetitions is difficult. Galaxies evolve, their appearance changes. Light travelling along different routes could show the same object at very different cosmic ages, making the duplication surprisingly hard to recognise. Another possible test comes from the cosmic microwave background. If the universe were smaller than the observable region in certain directions, light from the early universe might have travelled through the topology in more than one way. That could produce correlated patterns appearing in widely separated parts of the microwave sky. Cosmologists have therefore searched for matching structures and repeated patterns in the cosmic microwave background that might reveal a compact global topology. So far, no compelling pattern has established that the observable universe wraps around in this way. That tells us something useful. If space does have a repeating finite topology, its characteristic scale is not obviously small compared with the part of the universe we can observe. But there is a fundamental difficulty. Suppose the repetition scale were vastly greater than the observable universe. Then no light signal would have had enough time to travel around the global structure and reveal the repetition to us. Our entire visible universe could occupy only a small patch within that much larger geometry. Every measurement we performed would show space to be locally flat. Every telescope could look outward without finding duplicated structures. And yet the full universe could still possess a finite volume. This is where the distinction between local information and global structure becomes especially important. Imagine living in an enormous landscape whose repeating pattern is so large that you can explore only a tiny fraction of one section. Nothing nearby would reveal that somewhere unimaginably far away, the arrangement eventually connects back to itself. The same challenge could apply to the cosmos. Measurements of curvature tell us how space behaves across the region available to observation. They do not necessarily reveal how every distant region of space is connected to every other one. That is why the remarkable flatness of the observable universe does not give us a simple answer to whether space is infinite. An infinite flat universe remains completely consistent with what we observe. It may be exactly what exists. But a sufficiently large finite universe with an appropriate topology could produce observations that look almost identical from our limited position inside it. The difference would only become apparent on scales beyond those we can presently investigate. So flatness is an important clue, but it is not the final verdict. Space may continue endlessly in every direction, or it may be arranged in a global pattern so enormous that its repetition is hidden beyond our cosmic horizon. Either way, there need not be an edge. And once again, the question of whether space ends turns out to depend not simply on how space looks nearby, but on the structure of the universe at scales we may never be able to see in full. One of the stranger possibilities in cosmology is that you could travel through space in what seems to be a straight line, and, after an unimaginably long journey, eventually return to where you started. No wall, no reversal, no sudden turn, just a continuous path through space that eventually brings you home. At first, this sounds like something that should only happen in curved space. After all, the most familiar example is Earth. If you travel eastward around the planet and keep going long enough, you eventually return from the west. The surface is finite, but there is no edge. That happens because Earth's surface is curved. But cosmic topology introduces a deeper possibility. A universe can wrap around globally even if its local geometry is flat. This is where the distinction between curvature and topology becomes essential. Curvature tells us how geometry behaves in a local region and across extended distances. It determines how lines, angles, and volumes behave. Topology tells us how the entire space is connected. Two spaces can therefore look almost identical locally, while being arranged very differently on the largest possible scale. Imagine, for simplicity, a two-dimensional world laid out like a flat square. Now suppose that moving through the right-hand side of that world causes you to reappear through the left-hand side. Then suppose that moving through the top brings you back through the bottom. There is no physical wall at any of these boundaries. From the point of view of the inhabitants, there may not even be a meaningful boundary there at all. Those locations are simply connected. If someone travelled far enough in one direction, they would eventually return to where they began. Locally, the world could remain perfectly flat. No one walking across a small region would detect any curvature. The unusual behaviour would come entirely from the way the full space was connected. In 3 dimensions, mathematically similar arrangements are possible. A space of this kind is described as multiply connected. That means there can be more than one distinct path connecting the same regions through the global structure of the space. Light could travel toward us along different routes. A galaxy could, in principle, be visible in more than one direction. An observer might unknowingly be looking at multiple images of the same distant object, produced because its light had travelled through different parts of the cosmic topology before reaching them. This has made cosmic topology more than a purely mathematical curiosity. Cosmologists have searched for observational signatures that might reveal whether the universe wraps around on itself. One possibility is to look for repeated structures. If the universe were compact enough, the same galaxy cluster or other distant feature might appear in several different parts of the sky. There is a complication though. Light does not show us objects as they are now. It shows us how they looked when the light began its journey. If one path through space were longer than another, then 2 images of the same galaxy could show it at different stages of its history. One version might appear young and active. Another could show the same system much later. That would make identifying the repetition rather difficult. A second test comes from the cosmic microwave background. Because this ancient radiation surrounds us in every direction, a compact universe could cause the same physical regions of the early cosmos to appear in more than one part of the sky. That could create matched patterns. Cosmologists have searched for correlated regions and matching circles in maps of the cosmic microwave background, produced by missions such as the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. If clear repeated patterns appeared in just the right way, they could provide evidence that space connects back on itself. So far, no convincing signal has shown that the universe has a compact topology on scales small enough to produce obvious repetition within the observable cosmos. That does not prove the universe cannot wrap around. It places limits on how small such a repeating structure could be. And this is where the problem becomes frustratingly difficult. Light travels at a finite speed. The universe also has a finite age. So if the characteristic scale on which space repeats is larger than the observable universe, then light may not have had enough time to travel around the topology and reveal the repetition to us. Imagine living inside an enormous repeating landscape. If the repeating pattern were only a few kilometers across, you could discover it easily. Walk far enough and the same places would return. But if the pattern repeated only after a distance far larger than anything you could ever explore, every observation would make the landscape look effectively endless. The universe could present us with the same problem. Our observable region is already roughly 93 billion light-years across in present-day moving distance. Yet the full spatial universe could be vastly larger. If a repeating cosmic topology only became apparent across distances far greater than that, then no telescope could currently expose it. The sky would contain no obvious duplication. The cosmic microwave background would reveal no matching pattern. And all of our measurements might remain consistent with ordinary infinite space. This means that the absence of observed repetition does not automatically establish infinity. It simply tells us that any compact structure must not reveal itself clearly across the scales we can presently observe. The Earth analogy helps again, but only up to a point. A traveller can circumnavigate Earth because the surface has positive curvature. In cosmic topology, return paths can occur in spaces with different kinds of curvature. A positively curved universe could close back on itself. A flat universe could possess repeating identifications. Even some negatively curved spaces can have finite global volumes through more complicated topologies. So wrapping around is not the exclusive property of one particular cosmic shape. What matters is how the entire geometry is connected. And that leads to an important answer to the original question about whether space ends. A universe could allow endless travel without providing an unlimited supply of entirely new space. You might travel forever without ever reaching a boundary, yet eventually revisit regions that were already part of your journey. The path could be endless while the total volume remained finite. There would still be no edge, no place where the universe stopped, no final wall floating in darkness. Space would simply connect back through its own global structure. Whether our universe actually does this remains unknown. Observations have not revealed a compact topology on the scales currently accessible to us, but geometry allows the possibility. And that means even an explorer who travelled for an absurdly long time might discover that the strangest thing about space was not that it ended. It might be that it quietly brought them back to the beginning. A literal edge of space is easy to imagine in one sense, because almost everything familiar to us has an edge. A room ends at its walls, a continent ends at its coastline, a planet has a surface, a galaxy fades into surrounding space. So if we picture the universe itself as an enormous object, it feels natural to ask whether there might be some final boundary where space simply stops. But this is where ordinary intuition begins to struggle. The edge of an object is not the same thing as the edge of space. A room has walls because it exists within a larger environment. There is space on one side of the wall and space on the other. A planet has a surface because the material making up the planet ends, while space continues beyond it. A cloud has a boundary because the density of material falls away into the surrounding atmosphere. Even a galaxy can have an outer region where stars become sparse, but there is still more space beyond the galaxy. These are all boundaries inside space. A literal boundary of space itself would be something much more unusual. To imagine it, suppose you could travel in one direction and eventually reach a final location. Beyond that point there would be no farther coordinate, no additional distance, no hidden region, no empty blackness waiting on the other side. Space itself would simply cease to continue. That sounds almost impossible to picture, because the moment we ask what lies beyond such a boundary, we have already introduced the idea of another location. And another location would be more space. The word beyond quietly assumes the existence of somewhere else. If there were truly no space beyond the edge, then asking what was outside it might be similar to asking what lies north of the North Pole. The question uses a direction that has stopped having the meaning we expect. Even that analogy is imperfect, because the North Pole is not an edge. You can continue moving across it. But it helps reveal the problem. Our language is built around objects existing in space, so trying to describe the termination of space itself pushes language beyond its usual purpose. Albert Einstein's general theory of relativity gives physicists a more precise framework. In general relativity, spacetime is treated as a geometrical structure. Events are represented within that geometry, and the relationships between them are described through spacetime intervals, curvature, and paths known as geodesics. Matter and energy influence that geometry, while the geometry influences the motion of matter and light. The standard cosmological solutions used to describe our universe do not normally require a material boundary enclosing spacetime. There is no outer shell built into the usual picture. Instead, a spatial universe can be infinite, or it can be finite while remaining unbounded. Either possibility avoids the need for a physical cosmic wall. This does not mean mathematics can never describe spaces with boundaries. Mathematicians can construct geometries with edges, boundaries, unusual identifications, and many other global properties. Physics can also consider spacetimes with special boundaries in mathematical models. But the existence of those possibilities does not mean the observable universe has such a boundary. A mathematical construction only becomes a good physical description when it is supported by evidence. And so far, observations have not revealed anything resembling a nearby edge to the cosmos. One clue comes from the large-scale appearance of the universe. When astronomers survey galaxies across enormous distances, they find structure everywhere. Galaxies form groups and clusters. Clusters connect through immense filaments. Between them lie enormous cosmic voids. The arrangement is irregular on smaller scales, but when averaged across sufficiently large regions, the universe appears broadly homogeneous. There is no obvious direction where the distribution of matter suddenly thins out, because space itself is approaching an end. The cosmic microwave background tells a similar story. This relic radiation reaches us from every direction. Its temperature is almost astonishingly uniform across the sky, with only tiny fluctuations carrying information about the early universe. There is no known hemisphere where the radiation abruptly behaves as though our line of sight is approaching a cosmic boundary. Instead, the large-scale universe appears remarkably isotropic. That does not prove that no edge exists anywhere. A boundary could, in principle, lie far beyond the observable universe. If it were sufficiently distant, no light or signal from it would yet have reached us. But there is currently no observational evidence requiring such a feature. And there are theoretical reasons why cosmologists usually consider other possibilities first. A physical edge raises difficult questions about the behavior of fields, gravity, radiation, and geometry near that boundary. Would matter be able to approach it? Could light reach it? Would a geodesic simply terminate? Would physical laws require special boundary conditions there? None of these questions is impossible to study mathematically, but they introduce additional structure that standard cosmology does not presently need. Instead, the boundaries that do appear naturally in cosmology are usually horizons. A horizon is not where space stops, it is where access to information becomes limited. The observable universe has a horizon because light travels at a finite speed and the universe has a finite age. Cosmic expansion can create additional horizons that determine which regions can ever exchange signals with us. These are genuine limits, but they are limits on observation and causal connection. Curvature provides another alternative to a literal edge. Space can bend globally. A positively curved universe could even be finite in total volume, while allowing an observer to continue indefinitely without reaching a boundary. Topology adds more possibilities. Space could have a repeating global arrangement, allowing distant regions to connect back to one another. And the simplest possibility remains that space may just continue without limit. All of these options are stranger than an ordinary wall, but they fit more naturally within the framework of modern cosmology. So when we imagine travelling to the end of space and reaching some final barrier, we are borrowing an idea from everyday objects and applying it to something fundamentally different. Walls are things that exist in space. Edges are usually boundaries between one region and another. But if space itself were to end, there would not necessarily be another region waiting beyond it. That is why modern cosmology generally replaces the simple picture of a cosmic boundary with subtler ideas. Horizons can limit what we see. Curvature can make space finite without ending. Topology can connect distant regions in unexpected ways. And infinite space would need no boundary at all. A literal edge is easy to picture. It is simply not what the evidence currently asks us to believe. There is a possibility that the universe we can see is only a very small part of a much larger cosmic structure. One of the main ideas that leads to this possibility is cosmic inflation. Cosmic inflation is the hypothesis that during an extremely early stage of the universe, space underwent a brief period of extraordinarily rapid accelerated expansion. This would have happened long before stars, galaxies, planets, or even atoms existed. The idea was developed in several important forms during the late 1970s and early 1980s. Alan Guth proposed an influential inflationary model while investigating problems in early universe cosmology. Other major contributions came from Alexei Alexandrovich Starobinsky, Andrei Dmitrievich Linde, Andreas Albrecht, and Paul Joseph Steinhardt. The details of inflationary models differ, but the central idea is simple. For a very short period, the scale of the universe may have increased at an enormous rate. This was not matter exploding outward through pre-existing space. It was an extremely rapid expansion of space itself. Inflation is important because it helps address several puzzling features of the observable universe. One of them is its remarkable large-scale uniformity. When astronomers observe the cosmic microwave background, they find that regions on opposite sides of the sky have almost exactly the same temperature. That is surprising, because in a simple non-inflationary picture, some of those distant regions appear to have been too widely separated in the early universe to exchange enough information or energy to become so similar. Inflation offers a possible solution. Before the rapid expansion, regions now separated by enormous distances could have been close enough to influence one another. They could approach a common physical state. Then, inflation stretched those once nearby regions across distances vastly larger than before. What now appears to be an enormous cosmic separation could therefore have originated within a much smaller connected region. Inflation also helps explain why the geometry of the observable universe appears so close to flat. A useful analogy is the surface of a sphere. A small sphere is obviously curved, but if the sphere became enormously larger while you could inspect only a tiny patch of its surface, that patch would appear flatter and flatter. Earth provides an everyday example. Standing in a field, the ground appears almost perfectly flat, even though the planet as a whole is curved. In a similar way, rapid cosmic expansion can stretch any initial spatial curvature over a vastly larger scale. The portion available to observation can then appear extraordinarily close to flat, even if the larger global geometry is more complicated. This has a remarkable consequence for the question of how far space extends. The entire observable universe may have developed from a region that represented only a tiny fraction of the space produced during inflation. Everything we can currently see, from the nearest stars to the most distant relic radiation, could occupy one limited patch inside a universe that extends vastly farther. How much farther is much harder to say. Inflation can make the total universe enormously larger than the observable universe, but it does not automatically prove that space is infinite. That distinction is important. A finite universe could undergo inflation and become unbelievably large while remaining finite. An already infinite spatial universe could also remain infinite throughout inflation. The theory concerns the evolution of spatial scales. It does not, by itself, settle the global topology or total extent of all space. So inflation may help explain why we see such a large, flat, uniform region without telling us whether there is ultimately a finite amount of space or an infinite amount. Some inflationary models go further. They contain a possibility known as eternal inflation. In these models, inflation does not necessarily end everywhere at the same time. Instead, some regions stop inflating and evolve into universes containing matter and radiation, while other regions continue to inflate. Because the still inflating regions can expand extremely rapidly, the overall process may continue indefinitely. This idea has led to scenarios in which many separate cosmic regions form within a much larger inflating structure. Such scenarios are often connected with the idea of a multiverse. But this is where the scientific footing becomes less secure. Inflation itself is a serious and extensively studied framework in modern cosmology. Certain broad predictions of inflation are compatible with important features of the observed universe, including near flatness and the properties of primordial density fluctuations. Eternal inflation is more model-dependent, and claims about a vast collection of inaccessible universes go further still. They are interesting possibilities, not directly observed facts. It is therefore important not to treat every consequence of every inflationary model as though astronomers have already seen it through a telescope. They have not. What inflation does provide is a physically motivated reason to suspect that our visible cosmos may be only a limited region of something much larger. The observable universe has a present diameter of roughly 93 billion light-years. That already sounds almost absurdly large. Yet if inflation occurred, even this immense region may represent only a small part of the total spatial extent produced by the early universe. There could be regions so far away that no signal from them has ever reached us. There may be regions from which no signal ever will. And because our knowledge depends on information travelling through spacetime, those places may remain permanently beyond direct observation. This creates an unusual situation. The universe may be far larger than the part available to measurement, yet the very mechanism that makes that larger universe plausible can also make much of it inaccessible. We can test inflation through its effects on the region we do observe. We can study the cosmic microwave background. We can measure the distribution of matter. We can compare models with the statistical pattern of primordial fluctuations. But we cannot simply look outside our cosmic horizon to check how much more space is there. So inflation does not give a final answer to whether space ends. Instead, it makes the scale of the question even larger. The region visible around us may not be close to the full universe. It may be only one small patch of a cosmic geometry stretched far beyond anything light has yet allowed us to see. And if that is true, the edge of our observable universe is not remotely the end of space. It is simply the point where our information runs out. There is a limit to how far we can see into the universe, but that limit is not a wall, a border, or a place where space suddenly stops. It is a horizon. More precisely, cosmologists use the term particle horizon to describe the greatest moving distance from which light or another signal could have reached us during the age of the universe. The word horizon is useful because it captures the idea of a boundary to observation without implying a physical edge. We are already familiar with horizons in everyday life. Standing on Earth, there is a limit to how far across the surface we can see. The landscape does not end there. Our view does. The cosmological version is created for a different reason, but the central idea is similar. The universe has existed for roughly 13.8 billion years, and light travels at a finite speed. That means information from sufficiently distant regions has simply not had enough time to reach us. At first, this can produce an apparently simple calculation. If the universe is 13.8 billion years old, perhaps the most distant thing we can see should be 13.8 billion light-years away. But cosmic expansion changes the answer. While ancient light has been travelling toward us, the universe itself has expanded. The matter that emitted some of the oldest radiation we receive today is therefore much farther away now than it was when that light began its journey. In present-day moving distance, the particle horizon lies roughly 46 billion light-years away. That produces an observable universe roughly 93 billion light-years across. The apparent contradiction disappears once we distinguish between light travel time and present distance. The light has not travelled through a static universe for 46 billion years. It has travelled for less than 13.8 billion years through a universe whose scale changed during the journey. One of the most important signals near the limit of what we can observe is the cosmic microwave background. This radiation was released when the universe was about 380,000 years old. Before then, the cosmos was filled with a hot plasma containing free electrons, atomic nuclei, and radiation. Photons repeatedly scattered from charged particles, making the universe effectively opaque. As the universe expanded and cooled, electrons combined with nuclei to form neutral atoms. Light could then begin travelling much more freely. The cosmic microwave background that reaches us today comes from that transition. When we map this radiation across the sky, it appears as though we are surrounded by an enormous spherical surface. This can easily create the wrong mental picture. There is not a physical shell wrapped around Earth. We appear to sit at the centre only because we are receiving ancient light from every direction. In one direction, we see radiation that began travelling toward us from a distant region. Turn around, and we see different ancient radiation that started from another region at roughly the appropriate distance. Together, those directions form what looks like a sphere around the observer. But the sphere belongs to our past light cone and our observational position. It is not a structure centered on Earth. An observer living in a galaxy billions of light years away would have their own observable universe. They too would see themselves surrounded by ancient radiation. Their particle horizon would be centered on their location. Some regions visible to them could lie beyond our particle horizon, and some regions visible to us could lie beyond theirs. This is another reason Earth cannot be interpreted as occupying the centre of the universe. We are only at the centre of the region from which information has had time to reach us. Every observer can say something similar. The particle horizon therefore moves with the observer in a conceptual sense. It is defined by causal history, not by a fixed boundary painted onto space. If we could somehow travel an enormous distance toward the present edge of our observable universe, we would not expect to arrive at a barrier. There would be no glowing surface marking the final limit. No cliff into nothingness. No sign politely explaining that the universe continues no farther. Instead, our observable region would change. From the new location, different parts of the cosmos would become available to observation. The horizon is determined by which signals can reach a particular observer, not by where space itself terminates. There is another subtle point. Some regions that currently lie beyond our particle horizon may become observable in the future. As cosmic time passes, light that has not yet had enough time to reach us may eventually arrive. In that sense, the observable universe can contain new information as the universe grows older, but cosmic expansion complicates the story. Because the expansion of the universe is accelerating, there are also distant regions from which signals emitted sufficiently late may never reach us at all. So the particle horizon is not the only horizon relevant to cosmology. Still, it captures the basic idea that observation is limited by causal contact. The present particle horizon marks the farthest regions whose signals could have reached us over cosmic history. It does not mark the farthest regions that exist. That distinction becomes especially important when thinking about the universe beyond what we can see. Suppose there is a galaxy presently located beyond our particle horizon. Its existence would not contradict anything we observe. The reason we cannot see it may simply be that no signal from that region has yet had enough time to cross the expanding space between us. The darkness beyond our observational limit, therefore, does not tell us that nothing is there. It tells us that no information from there has reached us yet. This is one of the simplest but most profound limits in cosmology. Astronomy depends on messages, light from stars, radio waves from galaxies, microwaves from the early universe, gravitational waves from violent cosmic events. Every observation requires some influence to travel from one place to another. If no signal has had time to reach us, then that region remains outside our direct knowledge. The particle horizon is therefore a boundary in information. It is not a boundary in existence. And that means the farthest thing we can observe today should never be confused with the end of space. Our vision has a limit. Whether space itself does is an entirely different question. There is another cosmic horizon that is even stranger than the limit of what we can observe today. The particle horizon asks how far away something can be and still have had enough time to send us a signal since the early universe. The cosmological event horizon asks a different question. If something happens in a distant region now, will information about that event ever be able to reach us, even if we wait for an unlimited amount of future time? The answer, surprisingly, can be no. Some regions of the universe may already be so distant, and the space between us may be expanding in such a way that signals emitted there now will never arrive at Earth. This possibility is closely connected with one of the most important discoveries in modern cosmology. For much of the 20th century, astronomers knew that the universe was expanding, but they expected gravity to slow that expansion over time. Matter attracts matter. So even if the universe continued expanding forever, it seemed natural that the expansion should gradually become slower. During the late 1990s, observations produced a very different result. Two teams studying distant Type 1 supernovae found evidence that the expansion of the universe had been accelerating. The Supernova Cosmology project was led by Saul Perlmutter. The High-Z supernova search team included Brian Paul Schmidt and Adam Guy Rees. Type 1 supernovae are extraordinarily bright stellar explosions whose observed properties allow astronomers to estimate cosmological distances. By comparing those distances with the redshifts of the host galaxies, the teams could investigate how the expansion rate of the universe had changed over cosmic history. The distant supernovae appeared dimmer than expected in a universe whose expansion was simply slowing down. The evidence instead pointed toward accelerated expansion. Saul Perlmutter, Brian Paul Schmidt, and Adam Guy Rees later shared the Nobel Prize in Physics for the discovery. In the standard cosmological model, the cause of this accelerated expansion is represented by something called dark energy. The name can make it sound more mysterious than the underlying observation really is. Dark energy simply refers to whatever component or effect is responsible for the present accelerated expansion within the cosmological model. Its fundamental physical nature is still uncertain. One possibility is the cosmological constant, originally introduced into Albert Einstein's gravitational field equations for a very different reason. In modern cosmology, a positive cosmological constant behaves like an energy associated with empty space whose density remains approximately constant as the universe expands. Other possibilities have been considered, but observations remain broadly consistent with a cosmological constant. Whatever its deeper explanation turns out to be, accelerated expansion changes the causal structure of the universe. Imagine light leaving a sufficiently distant galaxy and beginning its journey toward Earth. Locally, that light always moves at the speed of light. Nothing is slowing it down in its immediate surroundings. But while the light travels, the space separating large-scale cosmic regions is also changing. If the expansion continues accelerating in the way described by the standard cosmological model, there are sufficiently distant regions for which newly emitted light will never overcome the increasing separation. The photon keeps travelling locally. It never breaks the rules of relativity, yet it never reaches us. This is the essence of the cosmological event horizon. It is a limit determined not simply by how far light has travelled in the past, but by the entire future expansion history of the universe. That makes it fundamentally different from the particle horizon. The particle horizon concerns signals that have had time to reach us already. The event horizon concerns signals that can never reach us at all. This creates a curious situation with distant galaxies. We can currently see many galaxies that are already extremely far away. The light reaching our telescopes today left them billions of years ago. Seeing one of these galaxies does not mean that we will continue receiving information from every stage of its future forever. A galaxy can be visible to us now, while events occurring there sufficiently late in cosmic history may never become observable from Earth. The image we receive becomes increasingly ancient relative to the galaxy's own continuing history. As cosmic expansion proceeds, light from such galaxies is stretched to longer wavelengths and becomes increasingly faint. Over enormously long periods, many distant galaxies outside our gravitationally bound neighbourhood will effectively disappear from view. They do not suddenly cease to exist. Space does not end around them. They simply become causally inaccessible. This is an important distinction. A horizon can behave like a limit without being an edge. There is nothing solid at the cosmological event horizon. A spacecraft would not fly toward it and eventually collide with a transparent cosmic barrier. The horizon is defined by relationships between events in spacetime. If you change the observer, you would also change the relevant horizon. An observer in a very distant galaxy would describe their own region of causal accessibility. Earth would not occupy some universal privileged center. The same principle that applies to the observable universe applies here as well. The boundary belongs to what a particular observer can receive information from. It does not mark a place where reality stops. This gives the far future of the universe a quietly isolating character. If accelerated expansion continues indefinitely, gravitationally unbound regions become increasingly separated from one another. Galaxies belonging to our local group, including the Milky Way and the Andromeda Galaxy, remain connected because local gravity dominates their behavior. But more distant structures are carried progressively farther away by cosmic expansion. Over immense spans of time, observers in our future cosmic neighbourhood could inhabit a universe that appears much emptier than the one visible today. Many galaxies that currently fill our deepest astronomical images would no longer be detectable. The universe beyond them could still exist. There could still be enormous regions of space containing matter, radiation, and whatever structures survive into that distant era. But those regions would no longer be capable of communicating their later history to us. So the cosmological event horizon gives us something that can feel remarkably similar to an end. There are places whose future may be permanently hidden. There are events whose light will never arrive. There are regions that no signal sent from Earth could ever reach if the present pattern of accelerated expansion continues. Yet none of this requires space to have a boundary. The universe can become divided into increasingly isolated causal regions, while space itself continues far beyond each observer's horizon. And so there may be places we can never see, never contact, and never reach. Not because space ends there, but because an expanding universe can place part of itself forever beyond our reach. Beyond the observable universe does not mean beyond space. It does not refer to a hidden realm sitting outside reality, nor to some mysterious region where the laws of physics necessarily stop applying. It simply means parts of the universe that lie beyond the distance from which light or other signals have had enough time to reach us. That distinction is easy to lose because the phrase sounds much more dramatic than the physics behind it. When we look outward through powerful telescopes, we are looking backward in time. Light from distant galaxies may have travelled for billions of years before reaching Earth. Eventually, we reach a limit beyond which information has not had enough time to arrive. That is the boundary of our observable universe. It is a boundary in knowledge, not necessarily a boundary in reality. So what might exist beyond it? The simplest answer is also probably the least exotic. More universe, more galaxies, more dark matter, more enormous regions of gas, more clusters and superclusters, more cosmic voids, more radiation, and more large-scale structure extending into regions whose light has simply not reached us yet. This expectation comes partly from the cosmological principle. On sufficiently large scales, the universe appears approximately homogeneous and isotropic. Homogeneous means that one sufficiently large region is broadly similar to another when averaged over enormous distances. Isotropic means that the universe looks broadly similar in every direction. Neither idea suggests perfect uniformity. The universe is full of variation. One direction might contain a massive galaxy cluster, while another points through an enormous void. But when viewed across sufficiently large scales, there is no obvious sign that Earth occupies a uniquely special region, or that the universe changes completely once we look far enough in one direction. This gives cosmologists a reasonable basis for expecting that the universe probably does not suddenly transform immediately beyond our horizon. There is no evidence that galaxies stop. No observation suggests that matter reaches some abrupt final frontier. Nothing about the cosmic microwave background indicates that our observable region is surrounded by a strange boundary beyond which physics becomes completely different. If we could somehow move to a location presently beyond our own observational horizon, the simplest expectation is that we would find another region of ordinary cosmological structure. There could be galaxies there whose light has never reached Earth. Those galaxies could contain stars. Some of those stars could have planets. Their surrounding regions could contain dark matter halos, intergalactic gas, galaxy filaments, and cosmic voids much like those found within the universe we already observe. But there is an important limit to how confidently we can say any of this. We cannot currently observe those regions directly. That sounds obvious, but it places a hard boundary on scientific claims. We can extrapolate from what we see. We can build cosmological models. We can test those models against every accessible observation. But we cannot point a telescope beyond the observable universe and check what is happening there now. So when cosmologists describe the universe as probably continuing beyond our horizon, they are extending successful models rather than reporting a direct measurement of those inaccessible regions. That difference matters. Science is strongest when it keeps observation and inference clearly separated. Within the observable universe, we can measure galaxy distributions, cosmic expansion, relic radiation, gravitational effects, and many other features. Beyond the horizon, we rely on whether the same physical description continues to make sense. And so far there is no compelling reason to place an abrupt end exactly where our ability to observe happens to stop. Doing that would make our horizon strangely special. It would mean that the universe just happened to end at the distance where information can no longer reach us. That would be a remarkable coincidence. The more natural interpretation is that the horizon belongs to the observer rather than to the universe itself. Someone living far away would have a different observable universe. Their horizon would be centered on them. They might see regions that are permanently hidden from us, while missing some areas we can observe from Earth. This alone strongly suggests that no single observational boundary can be treated as a universal edge. There are, however, more speculative possibilities. Some models of cosmic inflation suggest that regions far beyond our observable patch could have developed under conditions that differ from those we see locally. In certain versions of inflationary cosmology, different domains can emerge within a much larger inflating structure. Those domains might, in some models, possess different effective physical conditions. This is where ideas connected with eternal inflation and the multiverse sometimes appear. But these possibilities should be kept separate from the simpler claim that ordinary unseen regions probably exist beyond our horizon. The continuation of familiar cosmic structure is a straightforward extension of successful cosmological models. A vast collection of causally disconnected domains with different effective properties is much more speculative. The distinction is important because the farther a claim moves beyond direct observation, the more carefully its testability has to be considered. Cosmology often deals with structures far larger than anything humanity can physically reach. That does not make the subject unscientific. Scientists can still test global models by examining the consequences they produce within the region we can observe. A model of the early universe might predict a particular pattern in the cosmic microwave background. A model of cosmic geometry might predict particular relationships between distance and apparent size. A model of large-scale structure might predict how galaxies should cluster. If those predictions disagree with observation, the model can be constrained or rejected. But there is a difference between testing the observable consequences of a model and directly observing every region the model describes. No telescope has photographed infinitely distant space. No spacecraft has crossed beyond our cosmological horizon and reported back. There may always be regions whose detailed condition remains inaccessible to us. That is not necessarily a temporary technological problem. Depending on cosmic expansion, some places may remain beyond causal contact permanently. And this is where the phrase "beyond the observable universe" becomes much less mysterious. It is not a destination marked by some boundary in space. It is simply where our information runs out. The universe almost certainly does not arrange itself according to the limits of our telescopes. The galaxies we see do not know that Earth has reached an observational horizon. The laws of physics do not appear to become weaker as we approach it. There is no known transition from universe to nothingness. Instead, the horizon marks the farthest region from which information has been able to reach us under the history of cosmic expansion. What lies farther away may be ordinary. It may be enormous. It may contain structures whose light will reach future observers, but not us today. And some regions may forever remain hidden. We cannot honestly describe their detailed present condition as though we have measured it. But neither does their invisibility provide evidence that space ends there. The simplest picture is that reality keeps going after observation stops. Our horizon is therefore not the edge of space. It is the edge of what the universe has had time to tell us. There is a simple problem with trying to prove that space is infinite. We can only observe a finite part of it. Every telescope, detector, spacecraft, and experiment operates inside the region of the universe that has had enough time to exchange information with us. No matter how powerful our instruments become, they still collect signals that have travelled through a finite cosmic history. Infinity, however, is not finite. To prove that space continues forever, we would somehow need to establish what happens beyond every possible distance. That is not something an observer confined to one accessible region can simply check. This creates an important distinction in cosmology. Observations can be consistent with an infinite universe. They can make an infinite universe seem simple, natural, or even strongly favoured under particular assumptions. But that is not the same thing as demonstrating infinity beyond all possible doubt. Suppose astronomers measure the geometry of space and find that it is extremely close to flat. That is exactly what modern cosmological observations indicate. A perfectly flat universe with the simplest possible topology can extend infinitely in every direction, so infinity fits comfortably with what we see. But it is not the only possibility. A universe could possess a very slight positive curvature whose scale is so enormous that the observable region appears almost perfectly flat. Imagine standing on a sphere so large that the visible patch beneath your feet seemed completely level. The more enormous the sphere became, the harder its curvature would be to detect. The same principle applies to cosmic geometry. If future observations measure spatial curvature with greater precision and still find no detectable deviation from flatness. Cosmologists can place increasingly strong lower limits on how large a positively curved universe would have to be. In other words, they could say that if the universe is finite because of positive curvature, then it must be at least this large. Improving the measurement pushes that minimum size farther outward. But there is a crucial difference between saying something must be extraordinarily large and saying it must be infinite. No matter how large the lower limit becomes, infinity remains a different kind of statement. There is always, at least in principle, room for a finite geometry whose characteristic scale lies beyond our ability to measure. Topology creates another challenge. Even if space were shown to be exactly flat within observational uncertainty, that would not necessarily establish infinite volume. A flat universe could, in some mathematical models, have a compact global topology. Space could connect back on itself across distances so enormous that its repeating structure remained invisible from our position. Cosmologists have searched for signs of such a topology. One possible clue would be repeated images of distant astronomical structures. If light could reach us along more than one route through a compact universe, the same physical region might appear in different parts of the sky. Another approach uses the cosmic microwave background. A sufficiently small compact universe could cause the same regions of the early cosmos to appear in more than one direction, producing matched or correlated patterns in the ancient radiation. Researchers have searched for these kinds of signatures. No convincing evidence has established a compact cosmic topology on scales small enough to produce obvious repetition across the observable universe. That is useful information. It rules out or strongly constrains many simple compact models with characteristic scales that would be visible to us. But once again, there is a limit. If the characteristic size of the topology is substantially larger than the observable universe, then the repetition may simply lie beyond our horizon. Light would not have had enough time to travel through the full global structure and reveal it. The universe could then look indistinguishable from an infinite one throughout every region accessible to us. This possibility raises a deeper question. What if the total structure of space is fundamentally impossible for us to determine? That does not mean science has failed. It means the universe may contain properties whose observational consequences never enter our causal region. Science works by testing models against evidence. If two different global models produce exactly the same observable consequences within every region we can ever access, then distinguishing between them may become impossible in practice. There could be an infinite universe. There could be a finite universe so large that its curvature or topology never becomes detectable from Earth or any future observer in our causal region. If both possibilities remain compatible with every obtainable observation, then the difference between them may lie beyond empirical resolution. Cosmologists still use theoretical principles when comparing models. Simplicity matters. A model requiring fewer assumptions can be attractive. Mathematical elegance can guide research. Consistency with established physics can make one description more compelling than another. But none of these considerations should be mistaken for direct proof. A simple infinite model does not become physically certain merely because it is easier to write down, and a more complicated finite model does not become impossible simply because it is less convenient. Observational evidence remains the deciding standard wherever observation is possible. This is one of the quieter lessons of modern cosmology. There are things we know with extraordinary precision. We can measure the age of the universe to remarkable accuracy. We can observe the cosmic microwave background. We can estimate the average densities of ordinary matter and dark matter. We can track cosmic expansion across billions of years of history. We can test the large-scale geometry of space. Yet the total spatial extent of the universe remains uncertain. That uncertainty is not a sign that cosmology knows very little. Quite the opposite. It appears because cosmology understands well enough to recognize the difference between what observations actually establish and what lies beyond them. We may continue improving measurements of curvature. We may discover unexpected patterns in the cosmic microwave background. We may find evidence that favors a particular topology. Future theories of quantum gravity or the early universe may also provide new constraints. But even then, proving literal spatial infinity may remain fundamentally difficult. A finite observer gathering finite information is being asked to establish something about an unlimited totality. So space may indeed be infinite. Everything we currently observe is compatible with that possibility, but science has not demonstrated infinity simply by failing to find an edge. The universe may continue forever. Or it may be finite on scales so immense that its full structure never reveals itself to us. And for now, the difference between those possibilities remains one of the genuine limits of what the cosmos has allowed us to know. So, does space ever end? The clearest answer modern cosmology can give is that no physical edge of space has ever been observed. There is no known wall, boundary, or final location where the universe simply stops. What we do have is an observable universe, and that distinction matters enormously. The observable universe is the region from which light and other signals have had enough time to reach us since the early universe. Its present diameter is roughly 93 billion light-years in moving distance. That sounds vast enough to be everything. But it is not necessarily everything. It is simply the portion of the universe accessible to observation from our location. Beyond that horizon, space may continue for an enormous distance. It may continue forever. Or it may eventually connect back on itself through a global geometry that gives the universe a finite total size without creating any edge at all. Current observations cannot yet tell us which of those possibilities is correct. One of the strongest clues comes from the geometry of space. Measurements of the cosmic microwave background, together with other cosmological observations, show that the observable universe is extremely close to spatially flat. On large scales, distances and angles behave very nearly as they would in ordinary Euclidean geometry. That is entirely consistent with an infinite universe. If space is exactly flat and has the simplest possible global topology, then it can extend without limit in every direction. Under that picture, the observable universe would be only one finite region inside an unlimited spatial expanse. Travel outward for any distance, and there would still be more space. No final galaxy, no last coordinate, no boundary beyond which existence disappears. But near flatness does not prove infinity. A universe can be so gently curved that the portion available to observation looks almost perfectly flat. If the radius of curvature were vastly larger than the observable universe, detecting that curvature could be extraordinarily difficult. The universe could then possess a finite total volume while appearing essentially flat across everything we can currently measure. And a finite universe would not necessarily have an edge. This is one of the most important ideas in the whole question. Finite does not mean bounded. The surface of Earth is a simple lower dimensional example. It contains a finite area, yet there is no edge where the surface suddenly ends. A traveller can continue moving and eventually return toward the starting point. Three-dimensional space could, in principle, possess an analogous global property. The details would not be identical to Earth's surface, but the principle survives. Space could contain only a finite amount of volume and still offer no final boundary to reach. Cosmic topology adds even more possibilities. Topology describes how space is connected on the largest scales. A locally flat universe could, under some mathematical arrangements, still have a finite repeating structure. Travelling far enough in one direction might eventually bring an observer back through another part of the same global space. No curvature would necessarily be obvious nearby, no physical wall would appear. The universe would simply possess a global connectedness that could only reveal itself over immense distances. Astronomers have searched for possible signs of this kind of topology. Repeated images of distant objects could be one clue. Matched patterns in the cosmic microwave background could be another. So far, no convincing evidence has shown that the universe repeats on scales small enough to be obvious within the observable region. That leaves the simpler infinite picture entirely possible, but it also leaves open finite structures whose characteristic scale is simply too large for us to detect. Then there are the horizons. These are sometimes mistaken for edges because they mark real limits to what we can see or communicate with. The particle horizon exists because the universe has a finite age and signals travel at finite speed. It defines the greatest commoving distance from which information could have reached us over cosmic history. The cosmological event horizon is different. Because cosmic expansion is accelerating, there are distant regions from which signals emitted now may never reach us, no matter how long we wait. These horizons can place parts of reality permanently beyond our access. But they are not walls. They do not mark locations where space itself stops. They are boundaries of causal contact. A limit to information is not the same as a limit to existence. This distinction is especially important because the universe may be far larger than anything humanity can ever observe. Cosmic inflation provides one reason to take that possibility seriously. A brief period of extremely rapid expansion in the early universe could have stretched an initially connected region across scales vastly larger than our present horizon. Everything we can see today may therefore occupy only a small fraction of the full spatial universe. But inflation does not solve the question completely either. It can make a finite universe extraordinarily large. It can also be compatible with a spatial universe that is already infinite. It does not, by itself, tell us the total global extent. And this brings us to the central limit of the problem. We are trying to determine the structure of all space while observing from inside only one causally accessible region. We can measure curvature, we can study ancient radiation, we can map galaxies across billions of light years, we can test the expansion history of the universe and compare competing cosmological models. But every direct observation still comes from a finite part of the cosmos. If the global structure of space only becomes apparent on scales much larger than the observable universe, then that structure may remain hidden. So modern cosmology gives us a confident answer to one version of the question and an uncertain answer to another. Does space appear to end at a physical boundary? No. There is no evidence for such an edge. Does the entire universe have a finite total size? Possibly. Could it instead be infinite? Absolutely. Both possibilities remain compatible with current knowledge under appropriate global geometries. And perhaps the strangest part is that even if space is finite, there may still be no place where it ends. We might live in a universe that is unimaginably large, but limited, or one that truly continues forever. Either way, the edge of what we can observe is not the edge of reality. For now, the universe gives us horizons, it gives us curvature, it gives us topology, but it has not shown us an end. So, does space ever end? The most precise answer modern cosmology can give is that no physical edge of space has ever been found. There is no observed wall, boundary, or final frontier where the universe simply stops. But that does not mean scientists have proved that space is infinite. The total extent of the universe remains unknown. What we can measure directly is the observable universe. From our position, that region is roughly 93 billion light-years across in present-day moving distance. Yet this number does not describe the known size of all space. It describes the region from which information has been able to reach us during the lifetime of the universe. That distinction changes almost everything. The cosmic horizon exists because light travels at a finite speed through an expanding universe that is roughly 13.8 billion years old. We eventually reach distances from which signals have not had enough time to arrive. Our telescopes are not looking toward a wall, they are looking toward the limit of available information. The modern understanding of this expanding universe emerged gradually. Albert Einstein's general theory of relativity showed that spacetime could possess a changing geometry rather than serving as an eternal, rigid background. Alexander Friedmann discovered solutions to Albert Einstein's equations in which the universe could expand or contract. Georges Lemaitre independently developed an expanding cosmological model and connected it with the idea of a universe that had once been much denser. Observations associated with Edwin Hubble then helped establish the relationship between the distances of galaxies and their recession. Together, these developments replaced the older image of a static cosmos with one in which cosmic distances evolve. And importantly, that expansion does not point away from one unique centre. On sufficiently large scales, every observer sees the same broad pattern of distant structures receding. Space expands throughout the universe rather than rushing outward from one central explosion. Measurements of the cosmic microwave background have given us another powerful clue. This ancient radiation preserves information from when the universe was only around 380,000 years old. Its patterns allow cosmologists to test the geometry of space across enormous distances. The result is that the observable universe appears extremely close to spatially flat. But almost flat is not the same as proven infinite. A universe with a very large radius of curvature could appear almost perfectly flat across the portion available to us. And even exact local flatness would not necessarily establish infinite total volume, because topology introduces additional possibilities. This is why a finite universe does not necessarily require an edge. A familiar comparison is the surface of Earth. Its area is finite, yet a traveller can continue moving without encountering a final boundary. Three-dimensional space could, in principle, possess an analogous global property. A finite universe might curve back on itself, or possess another topology that allows space to remain continuous everywhere. There could be a limited total amount of space without any location where space simply stops. The alternative is genuine infinity. Space may extend without limit in every direction, with our observable universe representing only one finite patch of an endless whole. Current measurements are compatible with that possibility as well. Cosmic topology makes the situation even less certain. Space could be locally flat, yet globally connected in a repeating way. In some mathematical models, travelling far enough could eventually bring an observer back toward the starting region without any boundary being crossed. Astronomers have searched for repeated patterns in distant structures and in the cosmic microwave background, but no convincing evidence has revealed such a compact topology within the scales we can presently observe. Horizons add one final layer. The particle horizon limits what has been able to send information to us so far. The cosmological event horizon, associated with accelerated cosmic expansion, concerns something even more permanent. There are sufficiently distant regions from which signals emitted now may never reach us, even if the universe continues for an unlimited amount of future time. These are genuine limits to observation and communication. But they are still not physical edges. Beyond them, space may continue while remaining forever inaccessible to us. And this is where science reaches an honest boundary of its own. We can test cosmological models using the universe available to observation. We can measure geometry, expansion, relic radiation, and the distribution of matter with extraordinary precision. But regions permanently beyond causal contact cannot be inspected directly. When cosmologists describe space continuing beyond our horizon, they are extending models that work extremely well within the observable universe. They are not claiming to have photographed the whole of reality, so the answer remains beautifully simple and slightly unresolved. Space has no known edge. It may be infinite. It may instead be finite but unbounded, and the entire universe could be vastly larger than anything humanity will ever observe. The quiet reversal is that the universe does not need an edge in order to have a size. It does not need an outside in order to expand. And reaching the end of what we can see does not mean we have reached the end of space.